Hello everyone, welcome to the channel Golden Barrel Technologies Private Limited. This channel is dedicated to helping students and professionals build a strong foundation and clear career path in VLSI and semiconductor industry.
Hi, welcome to the knowledge series session on DFT. Before we start with DFT, let's understand the requirement of DFT. So when we have any manufacturing, we always tend to see some manufacturing issues or defects. There can be shorts between VDD to ground or VDD to any input or output or ground to any input or output or any shorts between input to output as well due to the chemical issues during the manufacturing process. So here if we see one of the example for a NOR gate, we see a non-defect structure in the left hand side whereas the defective structure in the right hand side. In this structure there is a short between the output leg to the input leg which is causing a fault for us. Whereas in the left hand side we have a clean manufacturing process which has led to a proper NOR gate. So when we have such manufacturing defects, so we need to find out if the defect exists. For that we need some design methodology to find out the defects. Now here comes why and what is DFT. So the DFT stands for design for testability. That means it is used to detect the same manufacturing defects with lesser number of time taken, patterns and higher test coverage. So just in case to give as an example, we saw that in the NOR gate, there were some defects due to manufacturing. So to detect such defects, we modify the design, we add some design in such a way that post manufacturing, we are still able to detect such defects. So that is DFT for us. Now we have two main pillars of DFT. One is controllability and one is observability. So what does this mean? So at any point of time, at any node or signal should be controllable and observable from primary input and primary output. By controllability, we mean any node should be able to be forced to 0 or 1 or any node should be controllable. Now when it comes to observability, we mean that any node should be observable. That means any state of logic should be able to propagate to the primary output. This is one of the example of controllability where to control node A, we are adding a muxing logic and a control input so that based on this control point enable, this is the original connection and this is my control point connection. So instead of using my control point connection, I am using the input which is added so that it is controllable. Now in this scenario, my node is not observable because the combo logic is hitting an analog macro, and since this is not the digital logic, so the faults or node is not observable. Now to make this observable, we need to add some digital logic so that the data or status of this logic is propagated. For that we are adding one non-functional flop so that this data or the status is captured and propagated to primary output, which is observability. Now the main process of DFT is converting the normal flip-flops in the design, that is the sequential elements in the design, to scan elements. Where this can be multiple methodologies. It can be a muxed scan, it can be LSST based, or any other mist. We have multiple methods to which we convert, but this process may not be as simple as we think. So it requires lot of DRC cleanups, which is called as scan DRCs. We need to consider the OCC connections, the requirement of the OCC, test compress or the EDT logics, IJTAG and equivalent PDL connectivities, wrapper insertion, in-test and ex-test number in accordance with compression numbers, non-scanless and expected scan elements. We need to gain more scan coverage. We need to review the scan reports and make sure that the scan insertion is clean for us. Now, once the scan insertion is completed, we do the pattern generation using ATPG methodologies, using algorithms like D or PODEM algorithms. And then we simulate the patterns. It can be either timing or no timing simulations, where timing simulation considers the delays. So then we hand off the patterns to tester. Now to give the overview flow of just the scan and ATPG and simulation activities. So when we start with the design, we do the functional verification. Then we do the MBIST insertion or any sort of BIST insertions. Post that, we do the boundary scan insertion at the IO logics to test the IOs. That means any input output pins has to be tested. To test that, the boundary scan is added at the package level, not at the block level. Then we have the synthesizable logic or the design. We verify the timing for it. We do the scan insertion on that. And after this is clean, we do the pattern generation, that is the ATPG. Then we simulate those patterns. So these are the main overview of the DFT which we need to know. So other than scan, ATPG and simulation activities, it is also important to understand the MBIST, which handles the memories, LBIST, which handles the logic relations, and the BIST for the logics instead of scan for few scenarios. OCCs has to be taken care. EDT or test compression has to be taken care. Wrappers has to be done. All this we have to make sure that these are tried, inserted, verified, and simulated. Now we also have few methodologies called as SSN, where it helps to reduce the routing and also reduce the IOs. Thank you.